I'm presenting a work today which is a part of our ongoing research efforts in silicon photodiodes. And I have been working with my colleague Dr. McFarlane's group for the last year or so on development of we call SPAD, which is single photon avalanche detectors in standard CMOS process. This work was done by our graduate students Habib and Farhan, and none of them is here today. So I'm presenting on behalf of everybody. So I have been working, my group has been working on development of CMOS photodiodes for detection of very low level of bioluminescence for the last 10 years. Since last year, Dr. McFarlane's group has been working on the development of the avalanche photodiodes. So we decided to collaborate on development of silicon photomultipliers that will eventually replace photomultiplier tubes, which is currently used in a lot of biomedical instrumentations, especially for scanners. So CMOS photodiode-based SPAD stands for single photon avalanche detector. The way it works, it is a reverse bias PN junction with very high voltage. It is usually used in Geiger mode operation, where the voltage or reverse bias voltage is exceeding the breakdown voltage of those PN junction. So under very high voltage, if a photon is incident in the depletion region of this photodiode, it will trigger the impact ionization and avalanche breakdown, which will be detected by the current produced by the photodiode. So in a way, it's very similar to the photomultiplier tubes. So it has several advantages. It can do enhanced performance by integration of this device with mixed mode circuits on the same chip. And obviously, it will result in higher level of integration. And there will be substantially reduced costs compared to the photomultiplier tubes. Currently, PMTs cost about $100 to $200 each. And if we can replace this by CMOS SPAD, the cost will be substantially reduced. It will also lead to the portability and maybe making handheld scanning devices. And obviously, there is another advantage of free running timing accuracy, and it is unaffected by magnetic field. So there are several applications like in fluorescence, bioluminescence image and detection, radiation detection, like in positron electron tomography. It can be used in DNA sequencing, cryptography, 3D acquisition, and protein analysis. So the way single photon avalanche photodiode works, it's a PN junction. So we use CMOS process. So in a CMOS process, a PN junction can be formed between a P diffusion N well, can be formed between N well and P substrate. So it is a reverse bias PN junction, and when the photons are incident, it produces impact ionization because of the high reverse bias or high breakdown, high voltage, which is close to the or above breakdown voltage in case of SPAD. And the local current density increases rapidly until it is quenched. So what is the quenching event? That whenever the avalanche breakdown occurs, it results in a very large amount of current. That current is flown through a resistor, which could be active or passive resistor. When the current flows through the resistor, it produces voltage drop across the quenching resistor, which reduces the voltage across the PN junction, and it gets out of the breakdown mode. There are a few different challenges that is associated with SPAD devices. One is the premature breakdown that prevents full volumetric breakdown. What it basically means that we use planar silicon processes, and near the the planar CMOS processes, the diffusion layers are not quite circular, so they have edges where the electric field is very high, and it can lead to premature breakdown at the corners of the depletion layers. It can also have a problem with something called dark current count rate, which basically is the device is under large reverse voltage, and there is no light. Even then, there is a thermal generated carriers which can cause avalanche breakdown. So this is known as the dark count rate, and number of counts or spikes per second is the rate of the dark count. And in addition to dark count, we also have another problem with this SPAD, that when it is completely quenched, then we have to reset the device. By the resetting process is done very quickly, then it can trigger what is called after pulsing. What basically means that some of those carriers which were trapped in the defect centers can be released, and it can cause another avalanche breakdown. So that is known as after pulsing. So in order to prevent, our group has actually published a paper last year's IEEE sensors, where we developed this active quenching circuit as well as readout electronics to accommodate the resetting time. But this work is totally based on optimization of the device. So this is showing the premature breakdown. This is a simulation that is borrowed from another paper by Wu. This is actually simulation using a device simulator. Shows that at the corners the electric field is high, and it causes premature breakdown at the corners of this device. So in order to improve the breakdown voltage of the devices, there are several different mechanisms people use. The most common one is the guard ring process. If a device is fabricated in a dedicated process, then guard ring is a good option. But in silicon CMOS process, especially with annual process, it is very difficult to get an N-type guard ring to prevent this premature breakdown. So the other method is to use a polysilicon gate. Hence the name is called perimeter gated single photon avalanche diode, or PGSPAD. So the polysilicon gate is placed on the top of the junction, and voltage is applied to the gate that modulates the electric field by creating a field-induced junction, which causes the corner electric field to further reduce, and as a result the breakdown voltage of the device increases. This is the picture of those three different types of devices that were fabricated and tested for this particular work. There is an octagonal device, a circular device, and this is a square devices. The devices were characterized for breakdown voltage and dark count rates. There are different sizes of the devices were tested. There are one device with 22 by 22 microns squared, another was 70 by 70, another 110 by 110 microns squared. Then different shapes were studied, circular, octagonal, and rectangular, as well as we have done different junction. There are two photodiodes, one between N-well and P plus layer, another one P substrate and N-well. So this is the test setup for the IV characteristic. So for the test, we used two SMUs. The source measure units were Kirtley 2400 source, meters, and they were current limited to prevent the breakdown of the damage done to the devices. And in this SMU actually sweeps the voltage across the anode and cathode of this photodiode while sensing the current through it. And the second SMU provides the control voltage. So this is the IV characteristic in the reverse breakdown, showing the breakdown at different, increasing gate voltage. We can see that device breakdown actually changes. The increasing the gate voltage, we are actually increasing the breakdown voltage device, which we expected. So these are the summary of the breakdown voltage for when the gate is at floating voltage, meaning no gate potential applied to it. And you can see there are different values of the breakdown voltage are obtained from different devices. There is one is 22.3 is higher than the rest, and this is because of the doping concentration between P substrate and N-well. And this being low, we all know that the breakdown voltage is inversely proportional to doping concentration. And the reduced doping concentration actually increases the breakdown voltage, as you can see here and here. Other than that, the other devices have got very, very similar breakdown voltage. There are slight variations, but that is nothing significant. So the size of the device did not make any significant impact on the breakdown voltage of the device, but the choice of the PN junction makes a whole lot of difference. So this is showing us a summary of the gate voltage versus the breakdown voltage for different devices. These top two are for the low doping cases, and these four are actually. And this is the summary that the breakdown voltage of the P P substrate N well is higher than the breakdown voltage for N well and P plus is expected. And what you also notice that the circular cross section has this higher breakdown voltage compared to the octagonal N squared, and the breakdown voltage for small device is slightly larger than the breakdown for large device, but there is no significant change. It could be some. And this is the curve showing an equation that is developed based on this curve fitting. When we applied the gate potential, as you can see, increasing the gate voltage, which is applied to the control gate, all the devices show the increase in the breakdown voltage. Next, we also characterize the device for dark count rate. And the dark count rate, as explained earlier, is the phenomenon that occurs when the device is under high bias voltage but under complete dark condition. There is basically DCR or dark count rate is caused by trap assisted thermal carrier generation, which is the predominant cases. But there is also, it could be due to band-to-band tunneling and trap-assisted tunneling as well as excitonic generation. And dark count rate is a measure of the noise, is the indication of the noise measurement for these types of device. So for the experimental setup, we use again these two SMUs, two Kirkley 2400 source meters. But then we also put a quenching resistance externally. It's a 100K quenching resistance. And we observe the voltage at this point, and which is indicative of the current spikes caused by the dark count or the thermal generation carriers. And then we looked at dark count rate for various devices under excess bias. Excess bias is the voltage we apply across this PN junction, which is higher than the breakdown voltage of the device. So excess voltage of 2 means it's 2 volt. As you can see, the dark count rate initially increases for all the devices. Around 3 volt, most of the devices dark count rate kind of stabilize. Is mostly because after 3 volt, this is due to the tunneling, trap due to tunneling phenomenon actually dominates, and the breakdown dark count rates kind of steadies. The one thing we have noticed that for the circular devices, we see a larger dark count compared to the other structures, and we're still trying to investigate why this phenomenon. But it is pretty much consistent between two different devices. This is showing the excess bias voltage as a dark count for 2 different types of devices, and as you can see, this larger device is showing a little bit less dark count compared to the smaller device in both cases. So, in conclusion, we designed and fabricated perimeter gated SPADs in standard CMOS process, and we characterized the device to study the junction breakdown at a dark count rate. We have observed that the circular device voltage than in octagonal or circular device or square device, should be square devices. And we also have noticed that the bigger devices show slightly better noise performance or less DCR than smaller device. But we also observed that the breakdown voltage increases if we apply control voltage, the control gate of this polysilicon control gate for the PGSPAD. Excess bias, if we increase the excess bias, this increases noise, and the gate voltage, applying gate voltage actually reduces the dark count rate for all devices. So for optimum choice of these 5 parameters we listed above, will allow a designer to choose the best performing device for a given application. This is a part of our ongoing work on silicon photomultipliers. So what we showed today is for individual devices. We have paralleled those devices with a quenching resistor in a CMOS configuration to obtain what we call silicon photomultiplier tube, which is equivalent to the photomultiplier tube we see in the vacuum tube technology. So that's all I have to say today. So thank you for your attention.